In this lecture, we will look at the shape of the Earth and how time is determined from celestial events. The goals of this chapter are to determine the size and shape of the Earth, discuss the Earth's rotation, define a day, state the difference between a solar day and a sidereal day, and define a year. In ancient times, the Earth was considered flat. It does not take much effort when you go out to sea or go to Kansas that the Earth looks flat. We want to explore the validation or contradiction of this appearance. In other words, is there evidence that supports or contradicts the flat Earth idea? Part of the reason for this lecture is to show evidence that the Earth really is a sphere. There are a number of these flat Earth believers out there. Not all may really believe the Earth is flat, but some actually do. This is to dispel this notion. The ancient Babylonians and Sumerians had a flat Earth belief. In Mesopotamian mythology, the Earth was a flat disk, floating in an ocean surrounded by a spherical sky. Contrary to some belief, Columbus had no doubt the Earth was round. He never thought he would fall off the edge of the Earth. His error was underestimating the size of the spherical Earth. By the 6th century BC, the ancient Greeks became skeptical of the flat Earth hypothesis. By the 3rd century BC, they were fully convinced of the spherical Earth and gave it circumference. Pythagoras was a mathematician, and to him the most perfect figure was a sphere. He reasoned that the gods would create a perfect figure, and therefore the Earth was created to be a sphere in shape. At first, there was no real explanation of how the Greeks came up with this conclusion, other than their observation of the change of the stars when they traveled. Pythagoras and Plato taught their students that the world was round, but they had no justification or proof. The round Earth theory didn't get a proper explanation until Aristotle, 384 to 322 BC, who made 3 important observations. Every portion of the Earth tends toward the center until by compression and convergence they form a sphere. This says that gravity is pulling down on everything. Create a pile of sand at the beach and it can only be made so high before the sides collapse. Gravity points inward, towards the center. Travelers going south see southern constellations rise higher above the horizon, and the shadow of the Earth on the moon during a lunar eclipse is round. This image shows Toronto from a distance across Lake Ontario. It shows the buildings and a small sailboat in the foreground. But look closely at the boat and the buildings. What is missing? The bases of the buildings and the hull of the boat are hidden. For a spherical Earth, we can calculate how much of an object will be hidden by the curvature of the Earth. These calculations, which you are not responsible for, show how to calculate the horizon distance, dB, and the distance to the top of an object of height HL for an observer, a height HB above sea level. The radius of the Earth is 6,378 kilometers. All heights are in meters and distances in kilometers. For an observer 6 feet tall, 1.7 meters, the horizon distance is 4.8 kilometers, or about 3 miles. This is a picture of the Chicago skyline from a distance of 2 miles. The ground and bases of the building are clearly visible. It is within the 3-mile distance. These are the tallest buildings in Chicago for reference. Here is Chicago from 8 miles. At 26 miles, the bases and ground are clearly missing. At 30 miles, the shortest buildings are no longer visible. At 33 miles, only the tallest dozen buildings remain visible. At 40 miles, only the 4 tallest buildings are still visible. The image below is a drawing showing roughly the scale of the hidden parts of the city. The Willis Tower is on the left. The John Hancock Center on the right of the drawing is out of the frame of the image. Here is an experiment that you can perform. Go to a place where you can easily view the sunrise or sunset over the ocean. Be sure to check local weather reports to know the time of day to expect the sunrise or sunset. If viewing a sunset, make your first measurement lying down on the ground and your second measurement while standing. If viewing a sunrise, do the opposite. From now on, I will explain only the directions for the sunset. Please make the necessary adjustments for the sunrise experiment. Before the sunset, get a friend to measure the height of your eyes while you are lying down and still able to see the horizon where you expect the sunset. Use kilometers for the measurement units. Prepare a stopwatch to begin counting. Wait for sunset. When the last bit of sun has disappeared, start the stopwatch and quickly get up and stand in a position that is directly above where your eyes were when you were laying down. You should be able to see the sunset a second time. Stop the stopwatch when you see the last bit of the sun disappear. Have your friend measure the height to your eyes in the standing position. If you are adventurous enough, you can calculate the circumference of the Earth using the given equation. The answer will be in kilometers. The two images are both looking at Polaris. Polaris is higher in the sky than the farther north you travel. South of the equator, Polaris cannot be seen at all. This is explained by the body of the spherical Earth blocking your view of Polaris. In 200 BC, Eratosthenes, the librarian at Alexandria, was able to measure the circumference of the Earth using simple geometry. At Syene, now Aswan, some 800 kilometers southeast of Alexandria in Egypt, the sun's rays fall vertically at noon at the summer solstice. Eratosthenes noted that at Alexandria, at the same date and time, sunlight fell at an angle of about 7.2 degrees from the vertical. Writing before the Greeks adopted the degree, a Babylonian unit of measure, he actually said a 50th of a circle. He correctly assumed that the sun's distance to be very great. Its rays therefore are practically parallel when they reach Earth. Given an estimate of the distance between the two cities, he was able to calculate the circumference of Earth, obtaining in modern units 40,000 kilometers, very close to the accepted value of 40,075 kilometers. These images are taken during a total lunar eclipse. Note that the shadow of the Earth on the moon is circular. No matter when the eclipse is seen or where the observer is, the shadow is always circular. Which shape always casts a circular shadow? Of course it is a sphere. These are power lines crossing Lake Pontchartrain in Louisiana. Notice the tops of the towers form a curved line and the bases disappear at a distance. If the Earth were flat, the tops of the towers would follow a straight line and the bases would get smaller but would always be visible. Going higher up, as in the space station, the curvature of the horizon becomes more pronounced. Geosynchronous weather satellites photograph the Earth daily. The images are that of a sphere. We conclude that the Earth must be a sphere. Does the Earth rotate? If so, how could we tell? The ancient Greeks were not convinced that the Earth rotated. There seems to be a point in the sky that all stars seem to rotate about. The image shows a camera image, but this motion is easily discernible with the naked eye. There is a star close to the center of the circle, the North Star or Polaris. So this is inconclusive. It could mean the Earth is rotating, but it could also mean the stars are revolving around the Earth. According to the Greek astronomer Plato, if the Earth rotated, objects in the Earth would be blown off due to the wind created by the motion. Since objects aren't blown around by a strong wind, Ptolemy concluded that the Earth does not rotate. Can the bird drop down and catch the worm if the Earth rotates? One of the arguments against the moving Earth was the following. Consider a bird sitting at rest on a branch of a tall tree. On the ground below is a fat, juicy worm. The bird sees the worm and drops vertically below and catches it. It was argued that this would be impossible if Earth were moving. A moving Earth would have to travel at an enormous speed to circle the sun in 1 year. While the bird would be in the air descending from its branch to the ground below, the worm would be swept far along with the moving Earth. It seemed that catching a worm on a moving Earth would be an impossible task. The fact that the birds do catch worms from tree branches seemed to be clear evidence that Earth must be at rest. Can you see the error in this argument? The concept of inertia is missing. You see, not only is Earth moving at a great speed, but so are the trees, the branches of the trees, and the branch the bird sits on, the worm below, and even the air in between. Things in motion remain in motion, so if no unbalanced forces are acting on them, they continue in that motion. So when the bird drops from the branch, its initial sideways motion remains unchanged. It catches the worm quite unaffected by the motion of the total environment. But not all believed the Earth was stationary. Aristarchus of Samos believed the Earth rotated. He was ridiculed for his belief. In 1851, Jean-Bernard Léon Foucault hung a pendulum in the Pantheon in Paris and showed Parisians that the apparent motion of the plane in which the pendulum bob swung was in fact due to Earth's rotation. In other words, the pendulum was swinging in a fixed plane with respect to background stars as the Earth turned beneath it, carrying the Pantheon and everything else around. Uniform circular motion is the motion of an object traveling at a constant speed on a circular path. The speed depends on the period and the distance from the axis of rotation. We approach this with the familiar: the speed of an object is the distance traveled divided by the time. For circular motion, the distance traveled is the circumference of a circle, 2 pi times the radius of the circle. The period t is the time required to travel once around the circle. The Earth rotates as a rigid body. That means the period of rotation is the same for every location on Earth, 24 hours. However, as Earth rotates, different latitudes travel at different speeds. The r in the speed formula is the distance from the rotation axis. Closer to the pole, you are closer to the rotation axis, and your rotation speed is less than near the equator. The change in speed with latitude causes the Coriolis effect. The latitudes closer to the pole are closer to the axis of rotation and have a lower speed. The tendency for any moving body on or above the Earth's surface, for example, an ocean current, wind, or an artillery round, to drift sideways from its course because of the Earth's rotation was explained by the French scientist Gaspard Coriolis. A projectile launched from the equator towards the north has a higher speed to the east than higher latitudes and will land east of a north path. Similar for projectiles launched towards the south. It will land east of a south path. If launched from the North Pole, it has the slowest speed and will end up west of the south path. This cannot happen if the Earth did not rotate. The wind patterns seen on the Earth are due to the Coriolis effect. Sailors have a special term for the calm equatorial regions where low pressure persists and little winds exist, the doldrums. Sailors also have a special term for the regions within the high pressure band where winds are light and variable, the horse latitudes. Places between the high and low pressure bands, on the other hand, experience rapidly moving air and are characterized by strong, dependable winds. Hurricane winds also exhibit the Coriolis force. The center of a hurricane is a low pressure system. Winds travel from high to low pressure. Northern hemisphere winds curve to the right as they move from high to low pressure, causing the winds to circulate clockwise around a high pressure system and counterclockwise around a low pressure system. In the northern hemisphere, the circulation of winds around a low pressure system is counterclockwise. In the southern hemisphere, the circulation of winds around a low pressure system is clockwise. So with the evidence presented, it seems that Aristarchus was right all along. We have established that the Earth is a sphere and the sphere rotates. So how do we define a day? The day is based on the rotation of the Earth, but how do we define a rotation? We can only define rotation if there is something to compare the rotation to. There are two possibilities, based on the observations of the Sun, which is known as solar time, and based on the observations of stars, which is known as sidereal time. Sidereal time and solar time are close, but not identical. Consecutive sunrises mark a day. Originally, it was thought that this motion was the result of the Sun moving around the Earth. We now know this is due to the motion of the Earth around its axis. A day is the length of time which elapsed between the Sun reaching its highest point in the sky on two consecutive periods. The day was divided into parts 5,000 to 6,000 years ago. You can divide the day with a gnomon, or a stick in the ground, also called a shadow stick. As the day progresses, the shadow moves. The passage of the day is marked by the length of the shadow. Egyptian obelisks were used as gnomons. The video shows the passage of a day. The link to the video is posted on Canvas. Before we continue, we need to introduce the idea of mechanical clocks. Time was measured with a solar clock, but this was rather impractical at night or on cloudy days. So the idea was to create a mechanical clock, one that doesn't depend on the sun. Among the first clocks was a water clock. A water clock is any timepiece in which time is measured by the regulated flow of liquid into or out of a vessel where the amount is then measured. As soon as people compared time measured by the sun and time measured by mechanical clocks, some discrepancies were found. A second and more practical mechanical clock is the pendulum clock, invented in 1656 by Dutch scientist Christian Huygens, shown on the right, and based on the drawings made by Galileo in 1637, shown on the left. The period of a pendulum only depends on the length of the pendulum, L, and g, the acceleration due to gravity, which for the Earth is 9.8 meters per second squared. The third type of mechanical clock is the atomic clock. Atomic clocks are extremely accurate. The most accurate atomic clock won't lose or gain a second in 15 billion years. Our day is based on atomic clocks. International Atomic Time, or TAI, is a high-precision atomic coordinate time standard based on the notional passage of proper time on Earth. A day is defined to be 86,400 atomic seconds. This is International Atomic Time Day. The video gives a little more insight into the workings of atomic clocks. The link is posted on Canvas. But the Earth's rotation is uneven when compared to atomic clocks. When comparing atomic time, or mechanical clocks, with the actual rotation of the Earth, variations were seen. An example showing the variation of the length of the day from 1972 to 2018 is shown. Units are in milliseconds per day. While it might not seem like a big number, it is cumulative. One day loses 1 millisecond. The next day loses another 1 millisecond. If this trend continues, at the end of the year, you have lost 365 milliseconds. These variations in the length of the day must be accounted for, or noon will not happen when the clocks say noon. The comparison of solar time and atomic time is defined by the difference between two timescales. The second timescale is UT1. This would be the average time in atomic seconds of the apparent motion of the sun in the sky from noon to noon, as determined by something like a gnomon. Really, we look at the meridian transit of the sun. In 1958, the difference between atomic time, TAI, and solar time, UT1, was set to 0 seconds. While the difference changes constantly, On 14th February 2019, the difference was 37.1 seconds. Clock time is the time your watch or cell phone displays. It is formally called UTC for Coordinated Universal Time. UTC takes into account the variation of the rotation of the Earth by adding leap seconds. Leap seconds are only defined to be integer seconds and are added when the accumulated variation of the mean solar day and atomic day exceeds 1 second. This cannot be predicted and is obtained by observations. The last leap second was added on December 31st, 2016 at midnight, based on TAI, but corrected so noon still occurs at noon. In 2019, TAI minus UTC is 37 seconds. A leap second is a 1 second adjustment that is occasionally applied to the Coordinated Universal Time, UTC, in order to keep its time of day close to the mean solar time, or UT1. Without such a correction, time reckoned by Earth's rotation drifts away from atomic time because of irregularities in the Earth's rate of rotation. All leap seconds are scheduled for either June 31st or December 31st. The image shows the clock on June 30th, 2015, when 1 leap second was added to the day. Simple observations show that the rate of motion of stars is not the same as the rate of motion of the sun. A sidereal day, based on the stars, differs from a solar day, based on the sun, because of the motion of the Earth about the sun. The period it takes a celestial object, not the sun, moon, or planets, to be highest overhead on 2 successive days is called a sidereal day. The ancient Babylonians, Greeks, Egyptians, and Chinese noticed that sidereal time and solar time were not the same. The star patterns change throughout the year. The sidereal day is slightly shorter than the solar day because the orbital motion about the sun means the Earth has to rotate slightly more than 1 turn with respect to the fixed stars in order to reach the same Earth-Sun orientation. Helical means before and near the sun. Around 3100 BC, the Egyptians developed a 365-day calendar based on the helical rising of Sirius. The Egyptians used the flooding of the Nile as their year. They also noticed that the flooding followed the appearance of the star Sirius, when first visible in the morning before sunrise. It is a simple observation to make that the sun changes position in the sky throughout the year at local noon. The winter solstice, roughly December 21st, marks the time when the sun is lowest in the sky at local noon for the entire year. The summer solstice, roughly June 21st, marks the time when the sun is highest in the sky at local noon for the entire year. The sun is seen to vary above and below the celestial horizon. A tropical year, also known as a solar year for general purposes, is the length of time that the sun takes to return to the same position in the cycle of seasons as seen from the Earth. For example, the time from vernal equinox to vernal equinox, or from summer solstice to summer solstice, is 365.2421875 days. A sidereal year is the time taken by the Earth to orbit the sun once with respect to the fixed stars, 360 degrees. Hence, it is also the time it takes the sun to return to the same position with respect to the fixed stars, after apparently traveling once around the ecliptic. It is equal to 365.256363004 days, or about 20 minutes longer than a tropical year. The difference between the tropical year and sidereal year is due to the precession of the Earth. Local apparent time, also called apparent solar time or sundial time, is what everyone used long ago when they told time by the sun. Noon was what most people still think is noon, when the sun crosses the meridian, that is, when the sun is due south for people in the northern temperate latitudes at its highest point of the day, and halfway between sunrise and sunset. The very word meridian is from the Latin for midday. When the sun or star is on your meridian, it has not yet reached the meridian of someone to your west, and it has already crossed the meridian of someone to your east. People do not record the same time at different locations. This didn't matter when travel and communication were slow. The problem grew more acute in the 19th century. The widespread use of telegraphs and railroads finally forced a change. How could you catch a train when every town and every railroad company kept a slightly different time? In 1883, the United States was divided into standard time zones. The rest of the world soon followed. In each zone, all clocks were set to the local mean time of a standard longitude. 75 degrees west for Eastern Standard Time, 90 degrees for Central, 105 degrees for Mountain, and 120 degrees for Pacific. Each time zone differs from its neighbor by 1 hour because those longitudes are 15 degrees apart, which is 1/24th of the way around the Earth. The map shows the various time zones of the world. Time zones are as much political as they are astronomical. The Julian calendar was introduced by Julius Caesar in 46 BC. The Julian calendar has a regular year of 365 days divided into 12 months. A leap day is added to February every 4 years. The Julian year is therefore, on the average, 365.25 days long. However, the tropical year is not exactly 365.25 days, and this led to errors. As a result of errors in the Julian calendar, the date of the actual vernal equinox had slowly, over the course of 13 centuries, slipped to March 10th, while the calculations of the date of Easter still followed the traditional date of March 21st. Our current calendar, the Gregorian calendar, was instituted by Pope Gregory XIII by papal bull in 24 February 1582. Every year that is exactly divisible by 4 is a leap year, except for years that are exactly divisible by 100. But these centennial years are leap years if they are exactly divisible by 400. For example, the years 1700, 1800, and 1900 were not leap years, but the year 2000 was. The change in the mean length of the calendar year from 365.25 days to 365.2425 days, a difference of about 10 minutes and 48 seconds, meant that calendars needed to be reformed. Great Britain and its American colonies reformed in 1752, where Wednesday, September 2nd, 1752, was immediately followed by Thursday, September 14th, 1752. This shows what a calendar in the United States, which was still part of Great Britain, looked like in the September of 1752. The chart lists the adoption of the Gregorian calendars for various countries. Greece didn't adopt the Gregorian calendar until 1923. Greenwich Mean Time, GMT, was defined to be the mean solar time at the Royal Observatory in Greenwich, near London. GMT was formerly used as the International Civil Time Standard, now superseded in that function by Coordinated Universal Time, UTC. Astronomers use something called the Julian date, a timescale based on GMT, or UTC. The Julian date is a continuous count of days and fractions since noon Universal Time on January 1st, 4713 BCE on the Julian calendar. The Julian date for 2000 January 1st is 2,451,544.5. The Julian date for January 23rd, 2019 is 2,458,503.5. CE stands for Common Era and BCE stands for Before Common Era, which you normally think of as AD and BC. On which day of the year does the sun reach its northernmost point in the sky? A. Vernal equinox, B. Autumnal equinox, C. Summer solstice, or D. Winter solstice. The answer is C. The summer solstice. Leap years occur because A. Earth's orbital period around the sun is decreasing, B. Earth's orbital period is approximately 365.24 days, C. The Gregorian calendar contains only 11 months, or D. Earth speeds up in its orbit when it comes closest to the sun. The answer is B. Earth's orbital period is approximately 365.24 days. The shortest day of the year for a person living in the southern hemisphere is A. Summer solstice, June 21st, B. Winter solstice, December 21st, C. Vernal equinox, March 21st, D. Autumnal equinox, September 22nd. The answer is A. Summer solstice, June 21st. These are some of the reasons for accurate time. GPS needs very accurate time for position calculations. The internet and cell phones also require accurate timings. In 1 second, an airplane travels 880 feet. By comparison, the International Space Station travels 4.8 miles. This is the observation path of an asteroid as seen from the ground as it passes in front of the star Regulus in the constellation of Leo. With accurate timing information, the shape of the asteroid can be determined. We found that the shape of the Earth is a sphere, that the Earth rotates, and we looked at how time is defined in terms of celestial objects, the sun and stars. We found the difference between astronomical time and mechanical time.